In a previous lecture, we had seen how certain system had a step response which had sustained oscillations as shown here by this orangish curve. For some other system, it had these blue lines which were oscillations, but these were damped oscillations. We see the yellow line where the system starts from 0, reaches 1, and tries to stay there. We had the purple line, which was slightly slower than the yellow line, but still reached 1. And then we had the green line, which was taking a which was taking a long time to move from 0 and reach to 1. We also saw or defined the notion of natural versus forced response in the previous lecture. So if I take a pendulum, I just give it a little push, it just comes back again to its original position because it dissipates energy it dissipates energy in terms of friction and comes back to its downward position. This we saw as in the definition of an unstable system where the system starts from theta equal to 180 degrees, the upright position, and comes back to this position. I start with an initial position which has, so there is no perturbation here. I just start with an initial condition at theta equal to pi by 2 and see that the pendulum again comes back to its downward position. Okay, so let's see some others. So this, I look at the same pendulum now. I am forcing it to stay on top. I can also force it to go to 45 degrees to the right and just stay there. I can also force it to go negative of 45 degrees and stay there. There could be a system. So, for example, look at this little system here. It's the mobile inverted pendulum mimicking a Segway scooter. It's on the top, and see what will happen if I just push it, right? Our first reaction would be it may just fall down. So let's see what happens here. So this is this pendulum, or this mobile inverted pendulum, which even after pushing refuses to fall down. So it is forced to stay at the upward position and forced in such a way that even small perturbations do not affect its stability. You see, it's a very large push. The system still somehow recovers and stays back. So this is about the forced response. I can force the system to go to 180 degrees on the top, 45 degrees, negative of 45 degrees. Not only that, if it is forced to be on the top, slight perturbations will bring back to the position where it was forced to stay. Now look at this mass spring damper example. So I start with a little initial condition, and I would want that the position of the mass goes to this number 10 on the horizontal axis. But what I see here is it just keeps on oscillating. It just doesn't know when to stop. It starts, it goes till 20, keeps oscillating, and just doesn't know what to do. In the second case, it starts from 0, goes till 15, and then comes back to the left of 10, goes to the right, and slowly settles down to the position of 10. We have another system, the same thing, where it just goes slowly to 10 and then settles down there. We also have a situation where the system is now very slow to move, but it just goes and stays there. Okay, so we have things now from sustained oscillations in this picture till oscillations which die down, till systems which have no oscillations, they just start from 0, go to 10 and just stay there. Or systems which start from 0, a little slower, go to 10 and still stay there. And this also mimicked the behavior here, sustained oscillations, damped oscillations, and systems like on the yellow, the purple, and the green curve, starting from 0 and slowly reaching 1 and then staying there. So we now know few things. We now know the notions of natural response. So I start with 90 degrees, it just goes back. I can force the pendulum to go to 180 degrees. And not only that, I can just force, once I force it to be at 90 degrees, whatever I do, it just retains, it just goes back to its upright position. Whereas In this case, it was at this upright position. I do a little perturbation, it just comes back. So nobody was forcing it to stay there. Now, with the help of a control law, I am forcing it to stay at these upward positions. And now I have situations where I can now see what these four graphs mean here. The first thing is the undamped case where I will have no resistance in my system. It's like I start with a pendulum at some arbitrary position, it just keeps oscillating like forever. Things which are underdamped, we will slowly quantify this, that my system reaches 10, but before that it goes a little further away from 10. It comes back to lesser than 10 and then keeps oscillating around 10 and just settles down there. Then you have systems which do not go beyond 10, but they start from 0 and slowly reach 10. So these are some nice things to begin with. Hello and welcome to this lecture number 2 of module 4 of the course on control engineering. My name is Ramkrishna. I am from Electrical Engineering, IIT Madras. So in the previous lecture, we saw response of first order systems, and we saw the effect of what happens when I just have a R, a L, and I think I had a I0 of something equal to 5. Okay. Now I do something more. I add a capacitor to this, the same circuit, and see what happens. Okay, now I know I'm kind of now expert at writing down these equations. Not only that, I can do the Laplace transform and write down the equations now in this form. Okay, now this is a second order equation. I know what kind of solutions exist, when are the solutions real, when are the solutions imaginary, and so on. So let's say I start, we'll do a little more detailed discussions later, but when underdamped, I mean that the roots are complex conjugate. And we know how they depend on the value of the discriminant and so on. So when I have an underdamped case, the solution, again, we have done this before, so I'll not spend time solving this. The solution will have a constant term, exponentially decaying term, and the sinusoidal term. And this is largely what causes the system to oscillate. And so this term causes the system to oscillate. This explains the oscillations, and this expect how the oscillations decay or the oscillations die down. Of course, these are all the constants which show up in the solution, but for now we know how to solve these equations. So I start from an initial condition. What I see is my current goes till 2.5. It goes to lesser than 0 and slowly settles down to 0. That there is some initial voltage in the capacitor, and that initial voltage will show up as currents, and the current will also slowly die down. A question for you is what happens when I have only a L and a C, with some say VC at 0 is say 1, and say maybe the initial current I at 0 equal to 0. How will this behavior look like? A question for you to think. Okay, now I know that, okay, I have some oscillations which kind of die down with time. In the underdamped case, and also the case of no sources. I go one step further, I add a voltage source. And again, this is easy. Now I know how to find the current given the voltage via the transfer function and so on. So my interest is to solve for I of t via I of s. I first do the go to the Laplacian domain. My differential equations become algebraic equations. I solve those algebraic equations, and now I also know the inverse Laplace transforms to get it back to the form which I want. I'll not worry about how the solutions will look like, but again, for the underdamped case, which essentially means that the roots of of the quadratic equation are complex and conjugate. Okay, then I have, okay, this is what I see. I saw in the first video, right, where, or one of the videos earlier, that the system starts from 0, it has to settle down at 1, but it doesn't, it overshoots, it goes to 1.2, it comes back to 0, goes a little below again, and then settles down at 0. This is the forced response. The unforced response, everything goes to 0. The forced response, I have a voltage source, it just goes to a value of 1 on the current. Okay, so again, we'll revisit what it means by natural response. Natural response is a zero input response, also called as the system's response to initial conditions, no external forces. So here, in the case of RLC circuit, I do not have any external voltage, but there might be some initial inductor currents or capacitor voltages. Inductor currents would mean there is some flux stored in the inductor, or the magnetic energy stored in the inductor, or capacitor stores charge, which manifests itself as voltage, and it stores electrical energy. And of course, with all other independent voltage and current sources set to 0. We know how systems behave now. We also saw a few animations and what does it mean by a natural response. Forced response is the system's response now to external forces with 0 initial conditions. Like I take a fan, it's at rest, I switch it on, it gains speed to reach to the steady state speed, as we have repeated this example multiple times. So in RLC circuit, this would be the response of a circuit to only external voltage and current source. I'm not worried at the moment about initial conditions. We also know about the transient versus the steady state. Transient is a part of the response that goes to 0 at time becomes very large. Mathematically, it would mean that the transient response are the ones which, as t goes to infinity, should go to 0. Steady state response is the response after the transient vanishes and as time goes to infinity. In my graphs, until here, I'm looking at my transient response, or until here as my transient response. So these oscillations die down, and what I'm left with is the steady state response. This also shows up in the solutions to the differential equations, right? So in the transient response, in the unforcing, the steady state response is only 0, right? So there is no transients in the system. Okay, so why are we interested also in second order system? And particularly, we'll spend a lot of time discussing second order systems. It turns out that many physical systems or engineering applications can be approximated or modeled by second order differential equations. And the behavior is governed, there is a natural frequency, there is damping, there are sometimes oscillations. We also can talk of resonance. And as we saw, the system can exhibit underdamped behavior, where the system oscillates before it settles down to a steady state value. Overdamped or critically damped systems, where the systems move from 0 and go to 1 gradually. And some are overdamped system might be very slow to be. If you see maybe a fan which is like 30, 40 years old, it really takes a lot of time to build up its speed. Where do these occur? And we have seen some examples of this, right? Of automobile suspension system, largely shock absorbers, or systems which isolate vibrations. Electrical systems, we will see in the future in our analysis on frequency domain of filter design. We look at oscillators and some examples also including inductive charging in electric vehicles. Biomedical applications, prosthetic limb design, rehabilitation-based robotics. Many of these systems can be understood by just their second order models. We'll see a little more or many more of this as the course progresses. For now, we will go a little bit into what constitutes this analysis. What is a standard second order system? In the first order system, we had one pole, we had the notion of time constant, and we saw how a car can go from 0 to 100 in either 3 seconds or 12 seconds, depending on the value of the time constant. So for a second order system, the transfer function is often represented in this form. And each of these has a very nice meaning here, and why I just don't write this as a constant. So omega is the natural frequency. So when I say natural frequency, let us take a case. Again, I'll talk a little bit of this in detail, but for now, let's assume that zeta is zero. Okay, it corresponds to the resistance. We'll see that soon. So if g of s equal to zero, the damping ratio is zero, then I have s square, sorry, omega n s square plus omega n square. Now this is a sine curve. Okay, therefore, if there is no damping, this will be the natural frequency. Just like if I take a pendulum, I just leave it at this initial position, it might just keep oscillating at some frequency. When there is no friction in the system, the second order system will just oscillate and oscillate at its natural frequency defined by this omega n. Okay, now given a transfer function, we are interested in what are the poles of the system. Okay, and the poles are typically now given. Yeah, again, if I'm looking at the complex conjugate roots in this form. Okay, now depending, of course, this is the general form of the solution, but depending on the value of zeta, the poles can be either real or complex conjugate. It can just be purely complex, also purely real, purely imaginary, or complex, depending. And each of these values of zeta will define whether the system is overdamped, critically damped, or underdamped. So now we will see, we have pictorially or have an intuition of what overdamped, critically damped, and underdamped mean. And we see how all these will have a relation to this damping coefficient called zeta. Okay, so if I go to a second order system, I am interested in situations where the roots are complex conjugate. So complex conjugate poles will now be of this form, S equal to sigma minus omega d, where omega d is given by this formula. So the denominator will correspond to something like this. Okay, so we have, let's look at each of these things now, right? We have the system damping ratio. This is a dimensionless quantity which describes the decay of oscillations during transient response. Okay, so this will largely see when I say what is a physical quantity that causes the energy to dissipate or the energy to decay or the system to decay. Let's take this little example here, right? So here I'm largely looking at this alpha. What is the term which causes this entire thing to decay? Okay, let's erase this and again look a little closer at this. So I have this quantity alpha, and this is responsible for the decay of those oscillations. Now this alpha is directly related to the resistance. If R is 0, alpha is 0, and I will just have sine omega t, just sustained oscillations, right? And omega d will also become omega naught. Okay, so now I have this alpha now captures how the system decays, and physically it would mean dissipation or resistance or damping in the system. Okay, so that is where we are now. The system damping ratio is a dimensionless quantity describing the decay of oscillations during a transient. It is the ratio of the actual damping to the critical damping. We'll define these terms also slowly. Natural frequency is what we saw. When zeta goes to 0, my transfer function will just be of the form omega n square or over s square plus omega n square. This will just be a sine curve with a frequency of omega n. Now I have omega d. This is the system damped frequency. What happens when the system has damping. So the angular frequency at which the system tends to oscillate in presence of the damping force is the system damped frequency. If I just see how it looks on the complex plane, so S will have components of sigma plus minus j omega. It will have a real term and an imaginary term. So here, this value of sigma is as follows. So sigma is zeta omega n. Again, this just comes naturally from solving these equations, right? Sigma is zeta omega n, and omega d is this quantity. Again, where does this come from? This just comes from solving s square plus 2 zeta omega n s plus omega n square. So if I just look at the standard solution to the quadratic equation, you'll have like minus b plus minus root of b square minus 4ac over 2a. Okay, so this sigma is omega n. Of course, there'll be a minus sign because this minus here. So I'll just get minus sigma. So this value of sigma will be zeta omega n. I have a quantity called omega d, which will now just be, again from the solution of equations, omega n square root of 1 minus zeta square. Okay, then I can have a little angle here, theta, and if I just draw a right angle triangle here, so sine of theta would be the opposite. In this case is sigma over omega n. So this is zeta omega n over omega n. So this theta will be equal to sine inverse of this theta. Some literature or some textbooks will also maybe use some other notation for this. So they will call this as phi. Okay, if this is phi, cos of phi, I can now write as cos of phi will be sigma omega n. So I'm looking at this triangle now. Cos of phi will be sigma omega n over omega n. That is, sorry, zeta omega n, right? Not sigma omega n. Cos of phi will be sigma over omega n. Sigma is this zeta omega n over omega n. So I can also call this angle phi as cos inverse of zeta. So you can either use this or this. I mean, books use that interchangeably, and both will lead to the same interpretation. Okay, so if I just look at what was forcing my systems to behave in a certain way. So okay, let me call this in the standard notation as g of t. We'll use g for all transfer functions from now. Okay, so this is where my system starts off with. So this is my transfer function of the second order system. I'm looking at 0 less than or equal to zeta less than 1. That is the reason why these general solutions now, if zeta is less than 1, this will become imaginary, right? And therefore I will have complex conjugate roots. Okay, so this is the underdamped case, and the impulse response is given by something like this. This is nice to see, right? So I have a exponentially decaying terms multiplied with the sinusoid. Okay, the first thing is if the roots are, if zeta equal to 0, which means sigma, which was equal to zeta omega n, sigma becomes 0, e power minus 0 becomes 1. I am only left with sine omega t. And when zeta equal to 0, my omega d also becomes omega n. It just oscillates at its natural frequency. So this is the behavior, right? Even in the earlier slides, we saw the orange curve. Right? Maybe I may just quickly go here. This is the undamped behavior. Or in picture, you can see here, right? The system starts and just keeps oscillating. Doesn't know when to stop, or even it knows where to stop, but it doesn't know when to stop or even how to stop. And as I keep increasing the value of zeta or the value of resistance, I will see that until my sigma reaches close to 1, that I have a response like this. And what is the critical point? So this behavior is seen for zeta, which is strictly less than 1. When zeta becomes 1, my roots are no, for zeta equal to 1, my roots become real, and then I no longer have an oscillated response. But for now, whenever zeta is between 0 and 1, I see a response which has damped oscillations. Okay, little more details. The actual frequency decreases slightly as the damping ratio increases. You can see from these plots, right, of how the frequencies also change. For very low damping, the response is quite oscillatory, whereas for very large damping, the system shows the oscillations try to die down. When I start from zeta equal to 0, I just keep oscillating. I keep on increasing zeta. This is a damping ratio, this is not the actual resistance. As zeta reaches 1, the oscillations show some sign of dying down. And then zeta greater than 1, there will be equal to 1 or greater than 1, there will be no oscillations. And this will also be as a little question. What will be the roots of this guy when zeta equal to 1? I'll answer this shortly, but think of this. Okay, now stability. Now I have a now nice notion of stability. Stability depends whether the natural response grows or decays. So here in one of these examples, the natural response was just growing. Here, the natural response was nicely decaying. Right? The system starts from some arbitrary initial condition, comes back to the position where it is supposed to be. By the way, this is also stable. I've kind of forced it to make in such a way that the upright position becomes stable with a control design. Right? So slight perturbations will force the system back to where it is supposed to be, where it was forced to be. So this is also stable, right? This is a system which is made stable at the upright position, which is naturally unstable. We will learn of those techniques soon. Okay, so what does it mean? So if sigma is less than 0, then the pole is in the right half plane, and things will not be very favorable to us because we all the time we would want poles to be in the left half plane. Okay, so for zeta equal to 1, as we saw the response, the system starts from 0, goes to some peak, and comes down to 0. It will not go like this and then maybe come down and do so. No oscillations here. And we call this zeta equal to 1 as the critically damped case. And the solution now looks something like this. You see, there is no sinusoidal term here. There's just an exponentially decaying term. In an earlier lecture, I had asked you a question: what happens to limit t going to infinity of this particular signal, e power minus t? Maybe we have an answer now, looking at the plots and otherwise. What happens when zeta goes more than 1? At zeta equal to 1, we saw there were no oscillations. The system was slowly settled down to 0 without holding any negative values. In this case, I see that, okay, my solution looks something like this. Okay, so what I can just see here is as zeta becomes very large, the system response is slower. You see the blue line, this reaches steady state faster than the green line. Okay, you can also look at it in general, right? Your system is very stiff, it has a lot of resistance, it will be very slow to move it to the steady state. Okay. Now, this was about the impulse. What happens in the case of a step response? What if my system is subject to a step input? I know my transfer function, my output will just be 1 over s over the transfer function, and then I have this nice, I know how to solve these equations now, right? So if I start with the step response for the underdamped case where zeta is between 0 and 1, I'll not go to the details of the solution, we'll just try to interpret what the solutions look like. So now I have again same thing. I have an exponentially decaying term and I have some sinusoidal terms. Okay, the response now we are a little more adept at visualizing this. For zeta equal to 1, my system goes till maybe some 1.7. It keeps on oscillating and then oscillations die down. As zeta increases, it goes to 1 point, maybe 1.5 and then oscillates around this point and so on. And as zeta increases to 1, we see that the oscillations are now of smaller amplitude. The amplitude of the oscillations becomes smaller and smaller. Okay, so this is for the underdamped case. For the undamped case, things are easier. It will be still be the same. I have y of s is something like this, where I'm looking at now zeta equal to 0, resulting into a solution of this form. The system knows it has to reach 1, but doesn't know how to stop. It just keeps oscillating around 1. This is how the graph of this will look like. It just goes from 0, it goes to 2. We'll also see why it goes to 2. Why doesn't it stop at 1.8? Or why does this graph stop at 1.8? Why does this graph stop at the second one stop at 1.6 and so on and so forth? This will be an interesting analysis. For now, when zeta equal to 0, it goes till 2 and just keep oscillating between it goes till 0 till 2, again 0 and 2. It knows it has to reach 1, but is unable. It's unable to force itself to stay there. Okay. Now when zeta equal to 1, again I have a response which is the solution of it looks like this. Okay, I'll see that there are no sinusoidal terms here. But you see that these two terms will just slowly exponentially decay to 0. Okay, or not exponentially decay, but they'll slowly rise to 1 because it's a step response. Go and then also see that there are, sorry. Okay, my slides jump to the end slide. Maybe my system wants to go to sleep. It's tired already, but we'll not let it. We'll force it to not go to the last slide. So here, the system reaches the value of 1 and there are no oscillations. Okay, as a little exercise, verify this. Via the final value theorem. Okay, then the similar behavior, what happens when zeta goes greater than 1, then we will see some similar responses, right, where the systems become slower and slower to respond. And for very large, so what happens when zeta goes to infinity in the limiting case, the system will never move. Okay, that's just a theoretical concept, but as the friction becomes larger and larger, you see that the system is difficult to operate. Okay, so this is where we have kind of understood a good qualitative representation of second order systems, why they were important, what kind of applications we can visualize. We saw the response of second order systems largely depends on how the system is damped. It's undamped, it's underdamped, it's critically damped or overdamped. Now, in the next lecture, we will try to answer some questions that we had. Why does this plot go until 2? Why does the first curve here go till 1.7, second curve go till 1.6, 1.5, and so on. So this we will do a little more quantitative analysis. This will help a lot in our uh, in uh, uh, in fulfilling our design specifications. Should I design system to be underdamped? Should I design systems to be overdamped? Should I design systems to be critically damped? Or it just doesn't matter. So we'll see some of those examples in the next lecture. Stay tuned and thanks for listening.